Hello everyone! In today's math tutorial video, we will be discussing the fundamental characteristics of any base number system. As one begins to explore other base number systems, such as base 5 or base 16, it can be helpful to remember that these 6 characteristics are true of any base number system, and they can help guide you in understanding new number bases and working arithmetic problems in said bases. I will give examples of each characteristic in base 10, base 5, and base 16. Feel free to pause the video or rewind at any point if you would like to see another concept explained again or would like extra time with a slide. Let's begin. Number 1. Any base has the same number of symbols as the number base. With those symbols, we can represent any amount. We often confuse the concept of numbers and symbols. It's important to realize that number means value. So if we see a symbol that we may usually call the number 10, in every base the set of symbols 1 and 0 have a different value, and it's not always a value of 10. So just remember that numbers and symbols are different. In base 10, the middle column of both of these charts, we have 10 symbols to use, and they are the symbols 0 through 9. Once we reach the symbol, or the value of 9, we run out of new symbols to use, so we have to start reusing what we have available. So to represent a value of 10 in base 10, we reuse the symbols 1 and 0. To represent a value of 11 in base 10, we reuse the symbols 1 and 1, and so on. We can represent infinite values with just those 10 symbols from base 10. Now in base 5, we have fewer symbols to use. We have 5 symbols, and they are the symbols 0 through 4. So once we reach the symbol or value of 4, and we want to represent a new value of 5, we actually don't have a symbol that looks like a 5 to use in base 5, so we have to reuse the symbols we have available. To represent a value of 5 in base 5, we reuse the symbols 1 and 0. To represent a value of 6 in base 5, we reuse the symbols 1 and 1. With those 5 symbols in base 5, we can represent infinitely many values. Base 16 can be a bit tricky, as we run out of our typical number symbols to use, and we start using alphabetical symbols instead. So in base 16, we still have the symbols 0 through 9 to use, but once we reach the value of 9, to represent a value of 10, we start to use alphabetical symbols. To represent a value of 10 in base 16, we have a symbol that looks like the letter A. To represent a value of 11 in base 16, we have a symbol that looks like the letter B. We can go all the way up to the value of 15 in base 16, representing it with a symbol that looks like the letter F. Once we reach the value of 16 in base 16, we have to start reusing our available symbols. So the value of 16 in base 16 is represented with the symbols 1 and 0. A value of 17 in base 16 is represented with the symbols 1 and 1. With those 16 symbols, both comprising themselves of letters and numbers, we can represent infinitely many values in base 16. So just remember, the base number equals the number of symbols available in the system. Number 2. The value of each place is the base times the previous place. In base 10, we're pretty familiar with our place values. We start with the ones place, move to the tens place, hundreds place, and so on. But if you didn't know the place values off the top of your head, you could remember that each place value is 10 times the last because we're in base 10. Another way these place values are commonly denoted are as exponents of the base. So in base 10, the ones place, we could also represent it as 10 to the 0 power. The tens place as 10 to the first power. The 100s place as 10 squared, and the 1000s place as 10 cubed. This pattern is the same regardless of base number. So in base 5, we have the ones place, or 5 to the 0 power. If I wanted to find the next place value, I would multiply the ones place by 5, and I would find the 5's place, or the 5 to the first power. Multiply that by 5, and I have the 25's place, or 5 squared, and multiply that by 5, and I have the 125's place, or 5 cubed, and that pattern could keep continuing on as long as I needed to. In base 16, we have the ones place, or 16 to the 0 power. To find the next place, I multiply that place by 16, and I have the 16's place, or 16 to the first power. Multiply that by 16, and I have the 256's place, or 16 squared, and multiply that by 16, and I have the 4096's place, or 16 cubed. And that pattern could continue on as long as I need it to. So just remember, the number of the base equals the base of your place values. Number 3, each place can contain only one symbol. This is really important in base number systems larger than 10. When we talk about base 16, if we had a number that had a value of 12 in the ones place, 0 in the 16's place, and a 3 in the 264's place, it would be incorrect to write the number like so. This is because I have two symbols in one place value. I have a symbol of a 1 and a 2 in the ones place. So if I was going back and looking at this number and I didn't have this handy chart, I would be really confused. I would actually think the 2 belongs in the ones place, the 1 belongs in the 16's place, the 0 belongs in the 264's place, and the 3 belongs in the 4096's place. This is a very different number than my original number. It is important because I am in base 16 to use the correct symbols to represent this value of 12. Remember that we do have alphabetical symbols to use, so 12 would actually be represented by the symbol C. So the correct way to write this number is 30C base 16. That way I only have one symbol in each place value. Number 4, the value of the numeral is determined by multiplying each digit by its place value and then adding these products. This concept is a lot like the concept of expanded form you may have worked with before. In base 10, the number 234 can be expanded and its value explained by the following formula. 2 times 100, since there's a value of 2 in the 100's place, plus 3 times 10, since there's a value of 3 in the 10's place, plus 4 times 1, since there's a value of 4 in the 1's place. When I multiply and add my products together, I find that the number 234 base 10 has a correct value of 234. The same concept applies to all other bases. If I wanted to find the value of 234 base 5, I would write the following equation. 2 times 25, since there's a value of 2 in the 25's place, plus 3 times 5, since there's a value of 3 in the 5's place, plus 4 times 1, since there's a value of 4 in the 1's place. So when I multiply and add my products, I find that 234 base 5 has a true value of 69. Same for base 16. If I had the number 5AC, I would write the following formula to find its true value. 5 times 256, since there's a value of 5 in the 256's place, plus 10 times 16, since the symbol A represents a value of 10 in the 16's place, plus 12 times 1, since C represents a value of 12 in the 1's place. When I multiply and add my products together, I find that 5AC base 16 has a true value of 1,452. Number 5, the value of the digit depends on its place in the numeral. We know in base 10 that the number 3 and the number 30 represent very different values. But why? So in the number 3, the 3 represents 3 groups of 1, and in the number 30, the 3 represents 3 groups of 10, so these numbers have a different value. Same concept with every other base number system. In base 5, 0, 2 base 5 and 2, 0 base 5 represent different values because in 0, 2, the 2 represents 2 groups of 1, and in 2, 0, the 2 represent 2 groups of 5. So these numbers hold different values. In base 16, 0A and A0 represent different values because in 0A base 16, the A represents 10 groups of 1, and in A0 base 16, the A represents 10 groups of 16s, so these numbers hold different values. So where the digit sits in the numeral determines its value. Number 6, 0 represents an empty place and 0 represents an actual amount with a place on the number line. In base 10, we're very familiar with the concept of 0 without even realizing it. Look at the numbers 502 and 52. Are they the same number, as in, are they worth the same amount? No. The 0 in between the 5 and the 2 is used as a placeholder of an empty amount so that we don't mistake the two numbers as being the same. The 0 holds an empty place for the tens place. In every other base, we will also use 0 as a placeholder. For example, in base 5, if I had a number that had a value of 2 in the ones place, a value of nothing in the fives place, and a value of 3 in the 25s place, it would be incorrect of me to write this number as 3, 2, base 5, correct? Because that would mean, although I still have a 2 in the ones place, I would actually have a 3 in the fives place and nothing in the 25s place, and that would be the incorrect number. So I still need to use 0 as a placeholder for this value of nothing in the fives place, so that when I write the number correctly, I write 3, 0, 2 base 5, and then every value is in its correct place. 0 still holds the same meaning and use no matter the base. All these characteristics we talked about today will hold true for every base number system, whether it's base 2, base 24, or even base 214. If you memorize and remember these basic base concepts, it will make working with new base number systems in the future so much easier. Well, thanks for stopping by and learning something new today. If you have comments or suggestions about future math videos, comment down below with what you would like to see. If you would like to talk more in depth about the subject or would like some extra help with the concept, stop by the Tutoring Center at San Juan College for some one-on-one time with a math tutor. Don't forget to subscribe to the Student Success Center's YouTube channel and check out San Juan College's Tutoring Center's Facebook page for video updates and updates about the Tutoring Center. Keep going and keep learning, and I'll see you next time.